And thank you, Noah, for the introduction, and also Dan for invitation and introduction. Really, I'm delighted to give this presentation today, which focuses on computed pulse wave signals and their relevance in the development of technologies to assess cardiovascular function. So let me start by saying a few words on the pulse wave signal. So the pulse wave is the product of the beating heart interacting with flexible arteries. So when the heart pumps blood into the aorta, the aortic wall is distended and compressed, and this generates a distension compression wave of the arterial wall, which is called the pulse wave, that propagates through the arteries. And the pulse wave leads to a rhythmical expansion and contraction of all arteries. So for example, it produces the pulse that we can feel in the wrist. And this pulsatile movement of the arterial wall produces changes in blood flow and blood pressure with time and space throughout the arterial system. So physically, this is a fluid structure interaction problem with a strong coupling between the fluid mechanics of blood flow and the solid mechanics of the flexible arterial wall. And this plot provides in vivo evidence of the pulse wave propagating in the cardiovascular system. So it shows typical pressure waveforms measured in vivo along the rabbit aorta in normal conditions, from the root to the bifurcation with the iliac arteries that perfuse the legs. And the slope of the line joining the feet of these waveforms shows clearly that a raise in blood pressure at the beginning of heart contraction propagates away from the heart and then gets reflected back to the heart. And we can also observe the propagation of the pulse wave by looking at some characteristic features of flow and area waveforms acquired simultaneously by MRI at 5 positions along the upper thoracic aorta of the human. So why do we want to study pulse wave signals? So what's really the motivation here? So these signals can be measured in vivo using a variety of devices and are influenced by the heart, vasculature, and also the respiratory and autonomic nervous systems. So that makes pulse wave signals a rich source of information to assess human health, including cardiovascular health. And here you can see some examples of different clinical devices that can be used to acquire pulse wave signals in different positions of the body. And nowadays, there are also wearable devices that enable measurement of pulse wave in daily life and outside the clinic. So this is the outline of my talk. So I will start by describing how we can simulate pulse wave signals using biophysical modeling. And then I will focus on how we can create data sets of simulated pulse wave signals that are representative of samples of real subjects. And finally, I will show the benefits of using in silico pulse wave data sets in the assessment of vascular aging and arterial hypertension from pulse wave signals. So let's start with biophysical modeling. So when it comes to arterial blood flow modeling, there are 3 main modeling approaches. So there are 3-dimensional, 1-dimensional, and 0-dimensional models. And they can all describe time-varying blood pressure and blood flow in the cardiovascular system, but with a different degree of accuracy in space. So we have 3D models that account for the variation in pressure and flow in the 3-dimensional space. 1D models only consider changes in pressure and flow along the axis of the vessel, and 0D models are space independent. So this makes 3D models more suitable for describing local features of blood flows, whereas 0D models are more appropriate to describe global features. Apologies for the background noise. However, 3D models are computationally quite expensive compared to reduced order 1D models and 0D models, taking off the order of hours, even days to compute the solution using high performance computers. So when it comes to simulating the effect of the propagation of the pulse wave on blood pressure and flow, we use the 1-dimensional formulation since it is a good compromise between accuracy and computational cost, taking off the order of a few minutes to compute on a standard PC. And in the 1D formulation, the arterial network is decomposed into arterial segments connected to each other at nodes. And each segment is simulated as a thin, deformable tapered tube whose properties can be described by a single axial coordinate x. And then using the physical principles of conservation of mass and linear momentum, and applying the list of modeling assumptions on the right, we can obtain a system of partial differential equations that govern blood flow in each arterial segment. So the variables of the problem are the cross-sectional area of the tube, capital A, blood flow velocity, capital U, and blood pressure, capital P. And there is a third equation, which is called the tube law, that relates changes in blood pressure to changes in cross-sectional area, taking into account the material properties of the arterial wall, such as the Young's modulus, which is a physical measure of arterial wall stiffness. So we solve these governing equations for each arterial segment using an in-house finite element method. And then to simulate blood flow in the arterial network, we need to connect 1D model arterial segments at several junctions. So we solve the junction problem. And we do that by enforcing conservation of mass, linear momentum, and often also conservation of energy so that we neglect any energy losses at junctions. And as for the boundary conditions of the arterial network, at the root of the ascending aorta, we prescribe the flow waveform ejected by the left ventricle as inflow boundary condition. And this waveform can be measured, for example, using phase contrast MRI or Doppler ultrasound. And then what about the outflow boundary conditions? So at each terminal branch of the 1D model network, we couple a zero-dimensional model, often a 3-element Wien-Kessel model, which simulates the resistance to blood flow and the flexibility of downstream vessels. So resistance is simulated by a resistance R, and wall flexibility by a compliance C, which quantifies basically, so it's defined as the change in blood volume per change in blood pressure, taking into account this flexibility of downstream vessels. So now, as with basically as any model, the next step is to assess the accuracy of in this case, the 1D, 0D formulation, to verify that we are solving the right biophysical equations to simulate pulse wave propagation in arteries. So we have carried out several verifications of 1D, 0D modeling, which I'll show you next. So first, we compare simulated pressure and flow waveforms against measured data in a 1-to-1 scale model of the systemic circulation made of silicon tubes. So in the middle of the slide, you can see a plan view schematic of the experimental setup. The thicker tube, which represents the aorta, is connected to a pump, simulating left ventricular contraction, and each terminal branch is connected to peripheral resistors. So in this experimental setup, and unlike in the human body, we could be as invasive as we wanted when measuring physical properties. So we measured basically all the input parameters to the 1D formulation. So we measured the length and diameters of all arterial segments, the material properties of the silicon that was used. So we measured the Young's modulus and also the viscosity of that silicon. We measured the density and viscosity of the fluid used to mimic blood, and the inflow boundary condition at the aortic root, and also the parameters of the outflow boundary conditions at each terminal branch. So we also then measure blood, we measure pressure. It's not blood, but the liquid, the pressure of the liquid that we had in this experiment, and also the blood flow in over 70 points in the silicon network. And we then ran the 1D model to obtain simulated pressure and flow waveforms in the network of silicon vessels and compare numerical versus experimental waveforms. So the plots show comparisons for blood pressure and blood flow wave at 2 points in the silicon network, but we had like about 70 locations. So these are just 2 examples. So we have the right carotid on the left and the thoracic aorta on the right. And we saw that numerical predictions for pressure and flow waveform, those are in dashed lines, were able to approximate corresponding experimental waveforms that are shown in solid lines. And we obtain average relative root mean square errors, smaller than 3% in pressure and 11% in flow rate for all points. So we have also verified the accuracy of the 1D formulation against pressure and flow data simulated using the 3-dimensional formulation in several idealized geometries of the aorta and other large systemic vessels. So the 1D geometries were obtained from the center lines of the 3D models, and diameters and wall thicknesses of the vessels were identical. So we try really to match as much as possible with 3D and 1D models. Also, the 1D and the 3D formulations also shared identical inflow and outflow boundary conditions, and also had compatible material laws. So these are the results for one of the models that we look into. So this is a model of the full aorta. So we have flow rate wave on the left and blood pressure wave on the right. And you can see in blue the results from the 3D model, in red the results from the nonlinear 1D model, and in black those obtained from a linearized version of the 1D model that actually enables analytical expressions for blood pressure and blood flow, although those are really very long mathematical expressions. And the key result here is that that 1D modeling, either a numerical or an analytical solution, leads to average root mean square errors relative to 3D model predictions smaller than 3% in both pressure and flow rate, indicating the ability of 1D modeling to simulate pulse waveforms with a reasonable accuracy, at least compared to 3D modeling, but at a considerably much smaller computational cost. We have also tested the accuracy of 1D modeling by comparison against in vivo data acquired in the upper thoracic aorta by MRI in a volunteer. So here, flow waveforms were acquired using gated PC MRI, and area waveforms were obtained using gated two-dimensional 2D Cine SSFP MRI, which actually provided dynamic area images on the same 5 planes as the flow waveform measurements. So we also acquire blood pressure in the carotid artery using applanation tonometry. So in this study, we had to reduce the number of arteries to have a model with a large number of parameters being subject specific. And we were also able to show, so first, that the 1D modeling can provide reasonable approximations, those are in red, to the in vivo signals in black. And second, that it is not necessary to have a large number of arterial segments to capture the main features of blood flow and area waveform in the aorta. And it's also important to know that 1D model errors for pressure and flow pulse wave were similar and almost identical in some cases to those obtained using 3D modeling, which are shown in blue. So for both 1D and 3D modeling, we obtain average relative errors smaller than 7% between simulated and in vivo flow and area waveforms. So I have shown you several verifications of 1D modeling against experimental, against in vivo, and 3D model data that have given us, but also other research groups, confidence in using 1D modeling to simulate pressure, flow, and area pulse wave signals, and then study clinically relevant problems. So next, I would like to show you how 1D modeling can actually be used to create data sets of simulated pulse wave. So first, I would like to introduce the rationale really behind data sets of in silico pulse wave signals. So the idea is the following: the development and testing of algorithms for analyzing pulse wave signals requires comprehensive data sets measuring large clinical cohorts. And unfortunately, acquiring these data sets is usually a complex task. And on the left of the slide, you can see some of the issues that we may encounter. So it is difficult to measure reference variables precisely. So for example, cardiac output or the Young's or arterial wall stiffness. It is challenging to study the influence of individual cardiovascular properties on the pulse wave. And this is because other properties may change concurrently. It is complex to measure pulse wave at all the sites of interest, particularly central arteries near the heart. And acquiring and curating the data is expensive and time-consuming. And also, in vivo measurements are subject to experimental error. So to facilitate this process, using one-dimensional blood flow modeling, we have created data sets of synthetic pulse wave signals that are representative of samples of real subjects under a wide range of cardiovascular conditions. And they are complementary to human data and address all the issues encountered in vivo on the left, despite obviously the obvious limitation of relying on modeling hypotheses. So I will now describe the methodology that we use to create a data set with over 4,000 subjects aged 25 to 75 years old under normal physiological conditions. And it consists of 5 main steps. So we follow this 5-step methodology that we specifically developed in my lab and which I will now describe in detail. So first, we simulated the pulse wave signals for a 25-year-old healthy subject that we refer to as our baseline subject. And the cardiovascular properties for this subject already existed in the literature. So using these properties, we could simultaneously simulate the following signals. So going from left to right, so we simulated blood pressure, blood flow velocity, luminal area, and PPG signals as well. So now let me say a few words about the PPG signal. So I haven't mentioned that signal before. So this signal is an optical signal that can be acquired by pulse oximeters in the clinic and by also wearable devices such as smartwatches. And we can do that in daily life. So in real subjects, the PPG signal is obtained by shining a light onto a tissue, such as the finger, and then measuring the light, which is either transmitted through or reflected from the tissue. So this varies with time as the volume of arterial blood in the tissue changes. And the attenuation of light due to the non-pulsatile venous blood and also other tissue components, as the sketch is showing, is relatively static. And that means that the pulsatility of the PPG signal can be assumed to be entirely due to arterial blood flow. So in this study, the PPG was modeled by calculating the volume of blood stored in the terminal Wien Kessels of the 1D model as a function of time. So the second step in our methodology to create a data set of in silico pulse wave consists of reviewing the clinical literature to determine how model input parameters change with age. And this is a summary of the literature review findings. So for each parameter, we have a mean value, and that's shown in solid line, and a standard deviation values in dashed lines indicating 1 and 2 standard deviations. And the pulse wave speed plot, which is at the bottom right here, shows the baseline wave speed as a function of diameter for each age. So third step, so for all parameters found in the clinical literature review, we did a sensitivity analysis to identify the parameters, and that's 1 per row in the figure, that strongly influence pulse wave. So we did that by increasing in blue and decreasing in red each parameter independently by 1 standard deviation from its baseline value, and then by assessing the corresponding changes in pulse wave morphology. For example, at the carotid artery on the left and the radial artery on the right of the slide. In the fourth step, pulse wave were simulated for a baseline subject at each age group using age-specific mean values for all parameters found when reviewing the literature. So as an example, the red circles indicate the mean values used to simulate the 45-year-old baseline subject. And in the final step, the 6 parameters previously identified as having a strong influence on pulse wave were varied at each age decade in combination with each other by plus or minus 1 standard deviation from their age specific mean values. So this resulted in 3 to the power of 6, which is about 730 subjects at each age, and a total of over 4,000 subjects in the data set. So once the data set was created, we verified that the simulated pulse wave signals were representative of samples of real subjects. So how did we do that? So we did this verification by comparing a simulated pulse wave with in vivo data from healthy subjects from the clinical literature. And here you can see comparisons in a few arterial locations showing similar changes in pulse wave morphology with age to those measured in vivo. And we also compared indices that can be calculated from the simulated pulse wave across age groups with corresponding in vivo indices from populations of real subjects. And here you have a few examples. So we found that the trends, and in some cases, even the values, actually in most cases, even the values, were similar between the two, the simulated and in vivo. And it is important to know that these characteristics or indices were calculated from the simulated precious wave signals or other pulse wave signals, and they were not imposed as input parameters to the simulation. So for the remaining of my talk, I would like to show some clinically relevant studies on how in silico pulse wave datasets can help us design and test algorithms of pulse wave analysis, including machine learning models, and also understand the potential shortcomings of existing technologies, and understand the mechanisms underlying hemodynamic observations. And we can do all of these for different age groups and across a wide range of cardiovascular conditions. And I would like to illustrate these applications with two clinically relevant studies. So these are the assessment of vascular aging and arterial hypertension from pulse wave signals. So let's start with vascular aging first. So aortic stiffness is an important biomarker of vascular health. And indeed, increased arterial stiffness has been shown to be an independent predictor of morbidity and also mortality from cardiovascular disease. And it is one of the biomarkers of vascular age. So if you are interested in this topic, I suggest having a look at the European Union Vascular Age Network, which is very active in studying vascular aging. Aortic stiffness cannot be directly measured in vivo, but we can use the velocity at which the pulse wave propagates in the aorta as a surrogate for aortic stiffness. And several methods have been proposed to measure pulse wave velocity from pressure or flow waveforms measured at two arterial sites. So for example, the arterial sites that are shown in the sketch on the left. So typical combinations of waveforms are shown in the center, and the sketch on the right illustrates the foot-to-foot method for estimating aortic pulse wave velocity using two pulse waveforms, which calculates the pulse wave velocity as the ratio of the distance between the two measurement sites to the time delay for the foot of the pulse wave to travel from one measurement site to the other. Distances are typically measured from surface markings, and time delays by identifying the feet of the two waves using pulse wave analysis. And using a database of over 3,000 virtual subjects, we could test existing foot-to-foot methods and show that only the carotid femoral pulse wave velocity is really an accurate indicator of aortic stiffness, which is in agreement with clinical studies. So we could also actually, because we had simulated data, we could provide a mechanistic explanation of why this is the case. So results on the left show that carotid femoral pulse wave velocity correlates well with aortic pulse wave velocity across a wide range of values of the precise aortic stiffness value for each subject that we really know precisely for each subject. However, on the right, we can see that brachial ankle pulse wave velocity overestimates aortic pulse wave velocity, since it is related to the stiffness and also the geometry of more peripheral muscular arteries than the aorta. We also found that carotid radial pulse wave velocity and femoral ankle pulse wave velocity do not capture aortic stiffening. They are therefore not so good surrogates for aortic stiffness, which is in agreement with some in vivo studies that have raised concerns about these biomarkers. So the carotid femoral method is an accurate method that is widely used in clinical research. However, it requires skilled operators to acquire the data, and therefore its applicability is limited to the clinic. So using a combination of in silico and in vivo data, we are now investigating methods to estimate pulse wave velocity from a single pulse waveform. For example, from the PPG wave measured in the finger or on the wrist using wearable devices such as smartwatches or smartphones. And the idea here is to use pulse wave analysis to identify fiducial points on the waveform by calculating first, second, and even higher order derivative of the pulse wave signal. And then from those fiducial points, indices can be calculated and then studied. So we have shown strong correlations with aortic pulse wave velocity of indices calculated from pulse wave morphology from the PPG signal. So we observed that all these three indices correlated with aortic pulse width velocity, with coefficient of determination values ranging from 0.65 to 0.74. And this indicates that these indices may have utility for assessing aortic stiffness in line with the findings of clinical studies. However, the R2 values for the reflection index and the stiffness index, so those are the first two indices on the slide, were lower when using only data from middle age. So those were the 45-year-old virtual subjects, and those are shown in red. So this suggests that these indices may be less useful for stratifying middle-aged patients, with only the modified aging index, so the third index, performing well both across the age range and when considering only middle-aged subjects. And using in silico testing, we could also study the physiological determinants of each index and provide a mechanistic explanation of why the third index is performing better than the other two. And this is illustrated in these lower plots. So the key result is that there are several cardiovascular properties in addition to pulse width velocity that influence the three indices, so such as heart rate and stroke volume and large artery diameter. And the third index was not strongly influenced by large artery diameter, and as a result performed better both across the age range and also when considering only the middle-aged subjects. So it may be used for stratification of middle-aged subject or patients. So our results also suggest that clinical studies should investigate the utility of pulse wave indices over a small age range as well as over the entire cohort. We have also investigated machine learning methods applied to a single pulse wave form. And in this case, in this study, we used the radial pressure waveform to predict aortic pulse wave velocity using both in silico and also in vivo pulse wave datasets, so combining in vivo and in silico. And we followed two approaches in this study. So either by using fiducial points extracted from the waveform as input to a Gaussian process regression algorithm, or using the whole waveform as input to a recurrent neural network with long short-term memory. And here you can see scatter plots of estimated versus measured pulse wave velocities, with the estimated value obtained using either Gaussian process regression on the left and recurrent neural network on the right. And these are the corresponding Bland-Ullmann plots. And the average root mean square errors for all the estimated pulse wave velocities for the over 3,000 in vivo subjects that we had in this study were smaller than 1.6 meters per second using a recurrent neural network, and a slightly larger, so 1.8 meters per second using Gaussian process regression. So in relative errors, these are around 15% errors. Now, how did we use the in silico data? So the in silico pulse wave data set allowed us to examine the machine learning models with an exact theoretical reference value of the carotid femoral pulse wave velocity for each virtual subject. And it also enabled us to investigate the effect on the estimated values of pulse wave velocity of adding noise to the radial pressure waveform, so that's the input signal, and to do that in a controlled way, so different levels of noise. So without any noise, the average root mean square errors for all the estimated pulse wave velocities using the recurrent neural network was smaller than 0.1 meter per second for the over 4,000 virtual subjects. And this increased to only 0.2 meters per second when 20% of random noise was added to the pressure waveform. So therefore, the error obtained in vivo has the potential to be reduced to much less than 0.5 meter per second when we are working, and we are now working on actually more improved machine learning models to achieve in vivo errors closer to the much smaller values that we can achieve in silico. This is important to realize the potential of using single point methods for accurate assessment of arterial stiffness. So, and we are doing this research by combining in vivo and in silico data during training. of the machine learning models. So let's now look into arterial hypertension. So that's the last thing I wanted to show you today. So we have combined in vivo and synthetic data or in silico data, right, to study the central blood pressure measured in the aorta next to the heart. And this pressure is the load that the heart has to overcome when it pumps, and hence is a highly prognostic cardiovascular risk factor. So for example, an increase in pulse pressure, so that's the amplitude of the blood pressure, as you can see in the sketch. So an increase in this pulse pressure leads to hypertension. And several clinical studies have shown that central blood pressure has a higher prognostic value than peripheral blood pressure that is typically measured in the arm at the GP. However, central blood pressure can only be measured directly by catheterization, which is costly and also has associated risk due to its invasive nature. So using a combination of in vivo and in silico data, we have developed methods to estimate central blood pressure non-invasively and identify biophysical mechanisms that underlie the increase in pulse pressure with hypertension. So we have developed a methodology to estimate central blood pressure from non-invasive clinical measurements using 3 types of reduced order models with increasing complexity. So we have 2 zero-dimensional models and one one-dimensional model of the upper thoracic aorta. So you have a sketch of those models on the right. And the input data is shown on the left, and is the blood flow pumped by the heart into the aorta, measured by Doppler ultrasound or PCMRI, the blood pressure measured in the arm using a standard pressure cuff, and for the 1D model only, also we require the anatomy of the aorta, of the upper part of the aorta, measured by MRI. And then from this input data, we can estimate cardiac and vascular parameters that are then fed into the 0D or the 1D models to produce the desired central blood pressure as output. So mathematically, these are simple models. We are not using full 3D models. And these models contain a small number of parameters so that we can make them subject specific. So we can calculate almost all the parameters. And we paid really particular attention to avoid any parameter, physical parameter redundancy, and also to have only parameters with a clear physical meaning. So not to have mathematical parameters, but parameters with a physical meaning. And this is very important to design algorithms that can be used in the clinic. And I will now focus on the results of that were produced by the 3-element Wien-Kessel model. So that's the model in the middle on the right. So here in red, you can see estimated central blood pressure wave using the 3-element Wien-Kessel model compared to reference measurements in blue. For in vivo, so this is in vivo data. So in vivo normotensive subjects at the top, and in vivo also, in this case, hypertensive subjects at the bottom. And although the model does not accurately reproduce the fine details in the pressure waveform, the pulse pressure, the amplitude of the blood pressure is reproduced accurately. And the pulse pressure is of particular importance for hypertension, as I said before. So we focus on assessing errors for the pulse pressure. And we did this using Bland-Ullmann plots, which enable the analysis of the agreement between 2 different methods. So for example, a new method and the gold standard method. So differences between the 2 measurement methods are plotted in these scatter plots or diagrams against the values obtained using the gold standard method. And in our case, the y-axis shows the difference between measured pulse pressure values and the estimated ones, and the x-axis shows the measured pulse pressure, so the reference value. Horizontal lines are drawn at the mean difference. So these are shown in solid lines. And the limits of agreement, the dashed lines, which are usually defined as the mean difference plus and minus twice the standard deviation of the differences. So here there are 3 plots, right? And this is because we use 3 groups of subjects for this study. So it was very helpful to first design and optimize our algorithms using a large data set of synthetic pulse wave before doing the final testing using real clinical data sets that are much smaller in size. And those are the data sets of normotensive and hypertensive subjects that I'm showing on the slide. The three Bland-Ullmann plots indicate that we can obtain reasonable errors for a wide range of pulse pressure values. And also in the in vivo data, so in the normotensive subjects, the normal physiology was perturbed using vasoactive drugs that had diverging effects on the heart and arteries to cover a wide range or a wider range of physiological pressures. So we use the 4 drugs that you can see in the middle plot: dobutamine, noradrenaline, nitroglycerin, and phentolamine. And we went also further than just proposing an accurate method for central pulse pressure calculation. So what we did is using the 3-element Wien-Kessel model, we could investigate the physical determinants of increased pulse pressure in hypertension, and to do that in a subject-specific way. And of particular clinical interest is the quantification of the relative contribution of arterial and heart properties to the increase in pulse pressure. And we found that left ventricular dynamics accounted for actually more than 50% of the increase in pulse pressure in hypertension. So cardiac dynamics are more important than vascular properties. They seem to be more important when it comes to increasing pulse pressure. And this is important because current antihypertensive drugs focus on altering vascular properties. But our study suggests that cardiac properties should also be involved in the treatment strategy. And now I'm gonna conclude. So we have seen that pulse wave signals, including the PPG signal, can be modeled accurately and efficiently using computational blood flow modeling, using 1D and 0D modeling. We have seen that data sets of synthetic pulse wave provide a quick and inexpensive route to initial development and assessment of pulse wave analysis algorithms, such as algorithms for assessing vascular aging and arterial hypertension. We can do that across a wide range of cardiovascular conditions, and also quite quickly and in an expensive manner. And lastly, testing using synthetic data simulated in silico enables us to understand physical mechanisms, underlying correlations that are observed from populations of real subjects. And also we can train machine learning models across a wide range of physiological conditions. And these data sets may also be useful for interpretability of neural networks models, which are big black boxes at the moment. And moving forward, in silico testing, combined with machine learning and the proliferation of wearable devices, provides new opportunities for assessing cardiovascular function within the wider population using pulse wave analysis. And with that, I would like to thank my group and funding bodies, which have all contributed to this research to some extent, and also the research collaborators contributing to the research. And I thank you for your attention.
Great. Thank you so much for your talk. Oh, hold on, let me turn on my video. I'm going to open this up to questions. I see that Dan has already asked one in the chat. I'll read it out loud. And then if you do have a question, please feel free to raise your hand. I'll invite you to unmute yourself so that you can ask that. But I'll just read out Dan's question here, which is, thank you for the great presentation. And he has a question: how translatable are the 1D modeling concepts to PWV in microvascular systems like that in skin? Or do some assumptions break down given the high number micron scale branching vessels?
Yes, yeah, no, that's a good question. No, I don't think that we can use this 1D modeling approach for the microcirculation because one of the assumptions is basically that the blood is a continuum, right? So and that's not true in the microcirculation. I'm not aware of any studies really using 1D modeling in the microcirculation. Yeah, but I think the reason is because maybe we would have to change really the governing equations, yes, to account for the differences, right, between large arteries and microcirculation, yes. Also, for
Great, thank-
example, we are considering blood to be a Newtonian fluid. That's another thing that in the microcirculation, right, needs to be changed, right? And I've seen maybe 1 or 2 papers using 1D modeling with non-Newtonian fluids, but not too many. Yes.
Great, thank you. Thank you very much. I'm going to invite David Steinman. I'm asking you to unmute, and then you can go ahead and ask your question.
Hi, Jordi. Nice to see
Hi,
you.
David. Yeah.
Great talk. A lot of my students are here. I strongly encourage them to come. I really enjoyed your talk. So I guess I have a couple of nerdy questions. My first question is, to build up your synthetic database, did I understand correctly that basically you've sampled this n-dimensional space of parameters by, at the mean and plus or minus 1 standard deviation? Did I get that correct?
Yeah, that's correct. Yes.
Have you thought about, or why don't you do something more stochastic than that so that you can capture the tails of those distributions?
Yes, that's a good point, right? So because we are doing plus minus 1 standard deviation, right? So basically we simulate the baseline models at each age group, and then we simulate variability, right, within this each age group by doing plus and minus 1 standard deviation, right? And then we look at all possible combinations of parameters,
Right.
the ones that have shown to be really in the sensitivity analysis that have been shown to change pulse wave morphology. But yes, perhaps we could do that as well. Yeah, so we would get a wider range, right, of
yeah, this is what I was wondering, because these simulations are cheap. I imagine the data analysis, even on 4,000 individuals, is cheap. So you could build up quite a large database that would cover a lot more of the variability, particularly if you're going to be interested in, trying to now see if you can discriminate between groups, because it's going to be the kind of the outliers that are going to be the most troublesome ones, probably. Yeah, so I was just curious if that was a...
Yeah, no, that's a good point. Yes, we did that 1 plus minus standard deviation. And that was for the first 2 data sets. Now we are introducing disease. So basically our virtual subjects are healthy, initially healthy, and now we make them sick, right? So we can put aneurysms and stenosis. And the reason why we can do that is because first we've checked actually that we can use 1D modeling to simulate pulse wave propagation across localized changes in geometry. For stenosis, we need an empirical model of energy losses, but we've done comparisons of 1D versus 3D, and it seems to be working well up to a certain level of occlusion, right, and size of aneurysm. But yeah, that's something we can check for next data sets to go to maybe 2 standard deviations as well. Yeah.
Well, I'm thinking more like, rather than sampling at those exact points, if you just, randomly filled, you've got Gaussian distributions essentially in all the dimensions. If you kind of randomly filled that space, I'm just wondering if that would give you, I don't know, more useful results, particularly when you're going to be trying to compare normal versus diseased. So that was just more of a, I mean, I'm not criticizing the approach you're taking, because we do the same thing with our UQ right now. We're going to start moving to stochastic sampling, but
no, it's a great suggestion. Thank you for that. Yes, and I guess that then you can do it also perhaps in a clever or smart mathematical way, right? That maybe
we're actually
simulations. Yes.
Yeah, there are apparently clever ways to sample that space. We're actually discussing that with my students. I can tell you about that offline. Just one other question I had about the noise that you added, because that was, as you were presenting, I was curious about noise. Have you considered adding, because you added noise basically in the amplitude, but I know like features like the dichrotic notch are particularly hard to capture, heart rate variability, like these are going to be real world issues. So how do you plan to model those?
So what I show you on the slides. So in that study, we added noise more on the amplitude, but also what we've done in another study is to add noise to to the Fourier harmonics. So to decompose into Fourier harmonics and then add noise in the frequency space as well. And yes, and that's something I think it can be improved, the way that we add noise. And in particular, this is really important for the PPG signal, right? Because in theory, this is a great signal, right? Because you can get it from those wearable devices. But the problem is that it suffers really from lots of artifacts, right? And noise and so on. Yeah, and there are lots of people doing research on that signal, on how to eliminate noise and so on. So yeah, it would be good, yeah, we are thinking of ways to do that. Yes, yeah.
And just practically, are these signals analyzed like per cycle, or are they somehow averaged over multiple cycles and then analyzed?
So in reality, the signal, so there are different ways of analyzing the signal. So you can do sort of take a window of PPG signals and then calculate an ensemble average, right? And also then eliminate signals that are not of high quality enough. And then you can do filtering. So there are different techniques that you can use in reality. But there are also techniques that basically, there's a technique called the attractor reconstructor, that you feed the whole window of signals, and it generates a 2D contour plot. It's a density plot that looks like sort of a triangle. That's the attractor. It's a mathematical concept. And it seems that it enhances some of the features of the signal, of the morphology of the signal, in terms of variability of the signal, and also in terms of within each bit, also morphology of the signal. So there are different techniques to analyze the signal, but also you can use machine learning, right, nowadays. And so there are those recurrent neural networks, for example, or we did, so we've looked at different machine learning models as well. Okay. So that's in reality, yes. In Silico, one important thing, here is that we are simulating only one cardiac cycle, right? And
that's what I was wondering. But you could easily simulate multiple cycles, heart rate variability, blah blah. So I really like it. I think it's a great opportunity to understand, the impact of things you can't measure on things you can measure. So I really enjoyed the talk. Thanks, George.
It's about trying to match, right, both worlds, right, in Silico and in Vivo. Yes,
exactly.
So that's what we're trying to do. Yes, thank you for your questions.
Sure.
Excellent. Thank you so much. I'll pause for a second. Oh, I see there is another question from Chris Baumeister, so I'll ask you to unmute.
Hi, Jordy.
Hi, Chris. Yes.
Great to hear your talk. Super fan of your work. I wanted to try to get a discussion with Dan and you going about sort of that last point with wearable tech, but I know Dan's got his voice issues. So, but yeah, I think like trying to get, that's something I've been interested in on the sidelines, is getting a better marker for arterial stiffness and trying to figure out ways to do that. So maybe that's conversation for another day. Maybe something kind of out of left field. To make a long story short, my colleague who teaches calculus at the University of Toronto wants to make these videos to help students prepare for these classes. So the audience is almost pre-calculus, and I was trying to think, all this pulse wave velocity stuff is really interesting, but it gets into complex mathematics pretty quickly. You have any thoughts on, like, if you had to, I don't know, tell somebody about all this wave action with the heart without using, with maybe like just high school mathematics? Any ideas come to mind?
Yes. Well, I'm thinking, yes. So I guess that perhaps you cannot ask students to run simulations, yes, because, well, at least our code is not that user friendly. But one idea would be to use this data set, right, of in silico pulse wave. Then you could play around with, so the code is available, so, and you can ask students to plot, right, different signals at different locations, but also see what happens when you change heart rate, when you change different parameters, right, cardiac or vascular parameters. And also I think now I cannot really provide details, but there are models, right? There are simulators that are more user friendly, but usually those simulators are designed using lamp parameter models, right? So, but they might be useful because sometimes they have the closed loop circulation, right? So they simulate also the chambers of the heart, so you can get pressure in the heart and volumes in the heart, right? And then in arteries, and so those could be useful also, and if they are user friendly, yes.
Yeah, thanks. That's a good idea. I know those guys in the Netherlands have the kind of an online model, and
yes,
seen like the CV sim and stuff like that. Yeah, maybe that's yeah, I'll think more about that. Thanks for the idea.
Yeah.
Great, thank you, Chris. I'm going to invite one of Dan's graduate students, Meg, to unmute himself.
Hi, thank you so much for a great talk. I guess a similar vein to the idea of like learning. So I'm a grad student with very little experience in silico modeling. So I'm wondering if you had any recommendations on maybe how to learn it, especially regarding to blood pressure estimation from PPG signals. I mean, I'm grateful that you share a lot of your data sets and they're publicly available. So just any ideas here on maybe how to start, how to go about this process here. Thank you.
Yes, no, thanks for the question. We do try really to provide supplementary material and codes and make everything available. At the moment, one thing that we are doing, I mentioned in one of the slides, I mentioned this vascular age network, which is a European project that is ongoing. So I mentioned it here, and I'm really actively, my group is actively involved in this network, in this project. And one thing that we are now about to submit is a review paper on post-wave modeling and analysis for vascular aging. And we in there we want to also provide a supplementary material. We want to provide in a single document like all the mathematical derivations of going from 3D to 1D, 0D models, and then different post-wave analysis methods that could be maybe useful for some people, more technical people. It's not available yet. Yeah, it might take a while to go through the revision process and so on. But the other thing, it's also, if you go to the website of this network, so you have it at the bottom, there are lots of webinars and yes, webinars and that are recorded. And if you are interested in post-wave signals, vascular aging, so maybe that helps a little bit. Don't know whether it answers your question, but sometimes it's difficult, right, to find material. Yes, and that's one of the aims of this network, to make material available.
Perfect. Thank you so much. I'll keep exploring your website, and I look forward to the review that comes out later on. Thank you so much.
Thank you for the question.
Excellent. Thanks so much. I'll pause for a minute just in case anybody else has any questions. This was such a wonderful discussion. So I want to sincerely thank Professor Alastruey for his time. I think this has been a wonderful series. This has been spearheaded by Professor Daniel Franklin, and this was his choice of speaker. And I'm so happy that we can have international speakers. This is one of the wonders of having these online seminars. I want to alert everybody to our next seminar. This is actually an in-person seminar on Tuesday, November 8th. We have Professor William Wagner, who is the director of the McGowan Institute for Regenerative Medicine at the University of Pittsburgh, joining us at TBET. But otherwise, thank you so much for everybody for attending, and thank you for your attention. I'll stop recording now, and I'll distribute the recording. If you do want a copy of it, feel free to send me an email. I can send you the link. And once again, thank you so much. This was a wonderful seminar, and such a great opportunity to be able to have this discussion with somebody all the way in Europe. So thank you for your time, and thank you for accommodating this time difference as well.
Yes, thank you, Noah. Thank you, Dan, for having me, and everybody for the discussion and the questions. Yeah, thank you.
Okay. Excellent. Thank you, everybody. I'll end the meeting now. So thank you again.